Oh, yes. Okay, so I've drawn a particular type of thermometer on the board here, and the way this works is we have a gas here. Say this is a glass tube, which is filled with gas over in the left chamber. It goes over here, like this whole region here with the dots. That's all gas, some kind of vapor. And the shaded section here is mercury. So you have some mercury in the left end, and there's a hose connecting the mercury from one end to the other. So mercury can flow between the two. Again, we have mercury in this column on the right as well. And we have this container here. Like, let's say we have water. Or let's say we have ice water here. Ice water is pretty cold. And so this bulb here, this gas that's exposed to this ice water, is going to come into thermal equilibrium with the ice water. It'll be at a temperature of 0 degrees Celsius. And we're going to talk more about gases later, but the pressure of a gas depends on its temperature. So right now it's cold and it's at a relatively low pressure. And so in this column on the right, we have gas pressing down on this mercury. Now, what happens if we replace this ice water with boiling water? So maybe to do this quickly, let's just say we release the ice, we take this beaker of ice water out, we had some boiling water prepared, we place this bulb in the boiling water. The temperature of the gas is going to increase. It's going to reach the boiling point of water, which is 100 degrees Celsius. And we know that the gas at a higher temperature is going to have a higher pressure. So we're going to have more pressure pushing down on this column. That's going to force this column down. The level of mercury here is going to drop down. And that'll push mercury from one column to the other. And then the mercury is going to rise here. And we define H to be the difference in height between the mercury in each level. And so we can say, let's say this pressure of the gas, let's call that PG. That's the pressure of the gas. So if we look at this reference level, let's say this tube has been evacuated over here, so this is a vacuum. So we don't have to worry about anything there. So the pressure pushing down on this level of mercury here, that's going to be the same pressure pushing upwards at this reference level. I guess we can just spell it out. Pressure of the gas. So like this reference level, the mercury here is pushing up with pressure equal to the pressure of the gas. Now, pressure is force over area. If we look at this column of mercury, the weight of this mercury, well, that would just be the mass of mercury times the acceleration due to gravity. And the pressure is a force over the area. So we're looking at the upward force. If we just look at a little layer of mercury right here, there's pressure from the mercury below pushing up. That's equal to the pressure of the gas. And above it, we have the weight pushing down. And those are equal to each other. So the pressure from this column of mercury above this reference line, that would be equal to the weight divided by the area. So A would just be the area of this cylinder. Now the mass here is the density times the volume. So we use rho, this Greek letter rho, to be the volume density. So rho would be measured, we're talking about a mass density here. This would be like kilograms per cubic meter in our basic SI units. And so if we multiply that by the volume, that would give us the number of kilograms, or the mass. Now, the volume of a cylinder is the area of the base times the height. You know, for any object where you have like this uniform cross-section, we'll call that cross-section area A. It doesn't matter what the shape is. As long as the shape doesn't change as you move up, then the volume is that area times the height. So the volume over the area is equal to H. So the pressure of the gas is equal to this weight, the pressure of this column of mercury above the reference line. And V over A is H, so we can write it this way. So the pressure of the gas is rho G times H, where H is the height of this column of mercury above the reference line. Okay, so why do we care about this? Well, this device here is a thermometer because H depends on the temperature. You know, we could put this in this mixture of ice water and, you know, this column will be a lot lower because H will be smaller. We can mark that down as 0. And then we put this in this boiling water mixture, or just this boiling water, let it come to equilibrium, and this column will rise. And so we can mark that down as 100. And so we have a thermometer that also measures the pressure of the gas. Because H, you know, we know the density, this rho is the density of this fluid, which we're saying is mercury. G is just, you know, the acceleration due to gravity. And H is the height, which we can measure. So we have a device that can simultaneously measure the pressure and the temperature of a gas. And there are limits to this, though, because if you cool a gas enough, eventually it's going to turn into a liquid, typically, or a solid. It's going to change state. Yeah, so we can only use this as long as the gas remains in this vapor state. So, basic idea, we can measure both the pressure and the temperature with the same device. So let's say we do that. So let's say that we have a particular gas in there. So we could, we had that, you know, that tube that had gas in the left chamber and then mercury in the right. It was that kind of U shape, upside down U shape with, like say, mercury in the right chamber. And so we can plot the temperature as a function of pressure. Let's say pressure, it's a force over an area. So we can say Newton per square meter. And temperature, let's say in Celsius. Let's see, I think I have a picture of this, which we can. Okay. Actually, yeah, let's change this so it matches the picture in the book. Okay. So yeah, we've got a picture of the device, but yeah, here we have, let's say we have a gas, and we can simultaneously measure the pressure and temperature at the same time. So if we do like one experiment, we'll get a dot on this thing. At a temperature of, this value, it's at a pressure here. And then let's say we do some more measurements, and we get more data points, and we can see that they follow this line. Basically, we're going to talk about gases more. Basically, in some sense, it looks like the pressure is proportional to the temperature. And I say in some sense because it's not this, well, we can say there's a linear relationship between them. Like changes in pressure are proportional to changes in temperature, but the zeros don't exactly line up here. If we go to a temperature of 0 degrees Celsius, we're still going to have some pressure in the gas, and we can keep going. And if we continue trying to measure this at lower and lower temperatures, eventually we're going to run out of data points because our device will stop working. At the very least, we'll get our gas to, even at low temperatures, it can stop behaving in the usual way when we get to very low temperatures. Usually we talk about something called an ideal gas, but at low temperatures it might deviate from that. But also eventually at low temperatures it's going to change into a liquid. And so we can't continue, then the device doesn't work. But if we could continue the trend, we can see that as we lower the temperature, pressure decreases. And it looks like if we were to go below some temperature, the pressure would become negative. And that doesn't make too much sense, because you can't have a negative pressure from a gas. The way a gas works, the pressure, we know a gas is made out of atoms or molecules that are moving around and bouncing off the walls. So if you look at a particular molecule, it'll hit this wall and bounce off. It exerts an outward force on the wall. And again, that force is very small, but there's a lot of molecules in here, and you have so many colliding, you don't feel, like if you have a balloon, for example, and you touch the side, you don't feel like all these little bounces, like all these little collisions with the individual molecules. You just feel this overall outward force. So the idea that a gas can exert an inward force doesn't really make any sense. However, our experiment's never going to show this happening. This seems to be linear, but at some point, the pressure would go to 0, except the gas is going to turn into a liquid before that happens. Okay. However, what if we use a different gas? So I'm going to draw what that might look like for a different gas. Yeah, for gas 2, if we were to continue and look at the line, we're going to get the same kind of thing. The pressure decreases as the temperature decreases. But what's interesting here is at this point where the pressure goes to 0, it is the same. And let's look at one more gas, say gas 3. If we fit this line to it, seems like they would all reach a pressure of 0 at the same temperature. And this temperature is minus 273 degrees Celsius. It's actually like minus 273.15 or something. Yeah. Anyways, I've got a picture of it here, like the thermometer, and that, like different gases. See, like the pressure always goes to 0 at the same temperature. And we call this temperature here absolute 0. So it's a temperature where every gas would appear to, reach a pressure of 0. Turns out there's a lot more significance to this number. So we have this idea, we call it absolute 0. We say that occurs at a temperature of minus 273.15 degrees Celsius. Now, it turns out that the name absolute zero is kind of well chosen because I mentioned laws of thermodynamics. So far, we've only talked about the 0th law of thermodynamics. But the 3rd law of thermodynamics, that's the last one, that basically says you can never cool an object down to absolute 0. And the basic idea is that, let's say that this is absolute 0, and you have an object that is above absolute 0. And if you want to cool an object down, you have to remove energy from it, and that energy can't disappear. So you have to put that energy into the environment. And normally things go from hot to cold. So if your environment, if you have something that's already very cold, you're going to have to remove heat from a cold object and put it into a hotter environment, which is like the opposite way things tend to go. So let's say we want to reduce the temperature a certain amount. We have to remove a certain amount of energy to cause this temperature to decrease. Now, let's say we do it again. We want to have the same temperature decrease. So we can make that happen, but it requires energy to do that. And the colder the temperature gets, the more energy that we have to expend to make this happen. And maybe another way of looking at it, let's say that we have this object and we remove a certain amount of energy that's going to cause a certain temperature decrease. And then if we remove the same amount of energy, that's going to be a smaller decrease. And then the same amount of energy again, the effect keeps getting smaller. And so it turns out that when you get to very low temperatures, you would have to use an enormous amount of energy to create even a tiny temperature change. Okay, so that's the basic idea. We can never cool something to this temperature, the negative 273.15 Celsius. And so that's why that name absolute 0 is well chosen. Kind of represents a lower limit. And I say it kind of represents a lower limit because actually it is possible to make things colder than absolute 0, but not by cooling it down until it's just below that. It's kind of a crazy way to make a system temporarily achieve a negative temperature, but we don't need to get into that. But the idea of just cooling things down, this represents an absolute limit. Okay. Now, because we have this kind of absolute lower limit, this is like a fundamental number. It represents something real about our universe, and so it's very good to have a temperature scale based on absolute 0. So remember we talked about different temperature scales like Fahrenheit and Celsius. We had these kind of reference levels that were just made up. Like let's use ice water and boiling water. Or some weird mixture of chemicals. Well, not that weird chemicals, basically ice and water and salt. And human body temperature. But now absolute 0 is something that's, fundamental level. We can see this as like a limit. That is built into the universe and not just something we picked out at random. And so there's a temperature scale based on absolute 0, and then it's called the Kelvin scale. Now, as far as we know, here we have, like, we can think of this as a minimum temperature. We don't have any known maximum temperature. So we still have this kind of, at least one of our reference levels has to be arbitrary. But what they've done is they took the scale and said, 0 degrees Kelvin is absolute zero. Otherwise, it's identical to the Celsius system. So let's go back to the picture we had before, but we're adding the Kelvin scale in. So here, this is freezing water. And here's boiling water. And let's say we have our Celsius scale, Fahrenheit scale, and now we have a Kelvin scale. So we know that absolute zero is minus 273, or yeah, I usually ignore that 0.15, but it's there. And so that's 0 on the Kelvin scale. Now, what they've done though is they've made they base the Kelvin scale on the Celsius scale just with this offset. So 0 degrees Celsius, so basically an increase in 1 degree Kelvin is exactly the same as an increase in 1 degree Celsius. And so here we have 273. And for 100 Celsius, we have 373 Kelvin. And again, these numbers are 32 and 212. I don't know exactly what T0 is, absolute zero on the Fahrenheit scale. It's like minus 450 Fahrenheit, I believe. So I'll look that up. Minus 459.67. Let's say minus 460. Now, converting between Kelvin and Celsius is very easy. One thing, remember in our temperature scales, so that Tc is our temperature in degrees Celsius. Tf is temperature in Fahrenheit. And T is temperature in Kelvin. So there's no subscript there. If you see a temperature of, say, 411, we just write T equals 411 K, and we don't even say degrees Kelvin. We'll just say 411 Kelvin. Now, if you want to say degrees Kelvin, I'm not going to really care too much about it, but the convention is we just say 411 Kelvin, and there's no subscript for the temperature. And Kelvin is the fundamental unit of temperature in the SI system. So it's related to Celsius, but not exactly. Now that we have this concept of absolute zero, so to convert to Celsius, we can say T equals Tc, and then it's either plus or minus 273. I don't even remember, but it's easy to figure out. I think we need a minus there. So yeah, if we have, or no, I think we need plus actually. Wait, let's think about that. Let's say we have a temperature of 0 Kelvin. That would be, we need plus. So if we're like absolute zero, the temperature in the Celsius scale is minus 273 plus 273. That gives us a temperature of 0. And again, you could come up with a formula to convert temperature from Kelvin into Fahrenheit or vice versa, but we don't really need to worry about that. If you wanted to convert to Fahrenheit, like say we had 55 degrees Kelvin. For the graphical approach, we wouldn't use a formula at all, but you could use our formula to convert that to a temperature in Celsius, and then just add 273 to get the temperature in Kelvin. So nothing really new or complicated about converting between Kelvin to Fahrenheit or Fahrenheit to Kelvin. Like you can use our formula to get Fahrenheit to Celsius, and then once you have that, to get Kelvin, you just add 273. So, yeah, these are the three temperature scales that we need to know about. There's actually another one called the Rankine or something. I forgot the name. But it's basically like an absolute zero, except based on the Fahrenheit scale, where like a change of 1 degree on that other system would be equal to 1 Fahrenheit degree change. I've never seen that used. I've seen it defined, but never actually seen it used. So just mentioning it. But these are the three that we need to know about. Now in science, the Kelvin scale is the most important because a lot of times a formula will contain temperature. And you have to be very careful. Generally, if your formula involves a temperature, you really want to be in the Kelvin scale. I can give you an example, which we'll come to soon. You might have seen this before. This is called the ideal gas law, where P is pressure, V is volume, N is a measure of how much gas there is, R is a constant, and T is the temperature. And T is the absolute temperature. That means a temperature based on this concept of absolute zero, like the Kelvin scale. And it's important that you're in Kelvin if you have a formula like this, because if you had something in, say, if you plugged in a formula in Celsius, you might be plugging in a negative number, which means you could have something like a negative pressure, or a negative volume, or a negative amount of gas, or something. You know, you can get ridiculous results if you're not in the right scale. So if you see a temperature in a formula, automatically think Kelvin scale. There's one exception to that, and then if you're talking about changes in temperature. Because changes in temperature, it doesn't matter if you're in Celsius or in Kelvin. You're going to have the delta T will be exactly the same if you're in Celsius or Kelvin. Like say you go from 55 to 75 Kelvin, delta T would be 20 Kelvin degrees. Whatever these numbers are, the change is still going to be 20 degrees. So, yeah, if you're talking about changes in temperatures, you don't necessarily have to be in Kelvin, but if you just see a T by itself, definitely want to be in Kelvin. Okay, so that's it for our temperature scales, and I think that's a good place to stop. Here.